In this video, we will get into a crash course in complex analysis so that we can understand all of the major theorems in complex analysis without going through all of the details of proving everything. So let's get started. Let's begin with the notation of the complex numbers. So we write the complex numbers with this blackboard bold C. And as a set, it's just equal to these combinations of a plus ib, where a and b are real numbers. Often we use the letter z for our variable in complex analysis, and the real and imaginary parts are written with x and y. Sometimes we also just like to write real part of z and imaginary part of z. And I'm assuming with this video that people are familiar just with multiplying complex numbers, so I'm not going to give the definition of multiplying them, but it is worthwhile to go through a few important identities. So the length squared of a complex number is just the sum of the squares of the two components of it, x squared plus y squared. But one important thing about complex numbers is that this can be expressed algebraically as z times z conjugate. And z conjugate is given here. So z conjugate is just taking our original x plus iy and flipping the sign on I. And just to see why this works, you could just do the multiplication. And the whole point of I here is that I squared is minus 1, so you multiply this out. I get x squared minus ixy minus plus ixy, and then I have minus I squared, so a plus y squared. So you do get x squared plus y squared when you multiply z times z conjugate. And this is useful for writing out the multiplicative inverse of z as z bar times the real number 1 over modulus z squared. And again, you can just check this, that if I do z times z bar divided by modulus z squared, we get what we want just by the formulas here. Okay, so no big deal there. And then you get this exact formula here for the multiplicative inverse. Now, the next thing to talk about is that we like to represent complex numbers not as just a plus ib, but we like to use the polar representation. So if z is given by x plus iy, we can use polar coordinates to represent x and y as r cosine theta plus I r sine theta. And when we write it this way, we factor out the r, and then e to the I theta is given as cosine theta plus I sine theta. And for right now, this can be considered a definition of e to the I theta, or if you do things kind of properly in a complex analysis course, you can define e to the z for complex numbers first and deduce an identity like this. For this crash course, we're not going to worry too much about what comes first, but e to the I theta does behave very much like an exponential. So we have these formulas down below. So the conjugate of r e to the I theta gives you r e to the minus I theta. And the point is that if I have a point and angle theta and a distance r that's also represented as x plus iy, then when I take the conjugate, it gets reflected down below to x minus iy. And so the length doesn't change, but the angle switches to minus theta. So that's why taking the conjugate, at least geometrically, gives you the negative angle. And e to the I theta satisfies these multiplicative properties, meaning if you multiply two of these exponentials together, you add the exponents, and we get standard power rules. So r e to the I theta to the n equals r to the n e to the I n theta. Next, let's get into the actual analysis part of it. So we're going to be working on domains here, and so for us, a domain will be a subset of the complex numbers, which we can view as R2, and we'll work with open and connected subsets, and that's what we call a domain here. This is different from just kind of the domain of a function. This is a definition that we're saying we want open and connected sets. And lots of times we have to use disks centered at places with various radii, so we have a notation for that. So the disk with center A and radius R is given with this notation. So this is the collection of Z, such that the distance between Z and A is less than R. We also have notations for closed disks. We might just write this for when we have a non-strict inequality. Okay, and what we're about to introduce are two seemingly different ideas, and they're going to be where we define the notion of analytic functions and define the notion of holomorphic functions, and then we're going to tell you that they're secretly the same thing by a non-trivial theorem. So analytic functions, which we'll define in a second, are defined using power series, and we're used to power series from analytic combinatorics, so let's get into it, but this is kind of the convergent power series where we do have to worry about things converging. So a power series centered at a point z0 in the complex plane is an infinite series of the form the sum from 0 to infinity of Cn z minus z0 to the n, where the coefficients here are complex numbers. And this converges if the partial sum sequence converges. And this is kind of the weakest form of convergence you could ask for, and we'll get into it later, but usually, we'll be more concerned with absolute convergence because it's a lot easier to work with. And soon we'll talk about some basic facts and maybe give some details to these ideas that power series converge basically on disks and diverge outside of a disk. So power series have a radius of convergence r, so it could be 0 and it could be infinity, where for z's within r of z0, the power series converges, and then if you're outside this disk, the power series diverges. And we'll get into the reasons for why this is a little later, but it's good to kind of preview this idea that power series make sense on a disk, and so you have to treat them as kind of living on a disk centered at the point you're talking about. Okay, so now here come the main definitions in complex analysis instead of just complex numbers. So a function f defined on a domain, and the function has values in the complex numbers, is analytic if for every z0 in the domain, you can find a disk centered at z0 inside the domain. So there is an r, a radius, so that there's a disk inside omega, and such that f is equal to a power series centered at z0. And the power series converges and is equal to f on this disk. Now let's look at a fundamental example of an analytic function, 1 over 1 minus z. So I claim this is analytic on the set the complex numbers take away 1. And to do this, we have to show that it has a power series representation at every point in this set. So the first thing we might do is, we might be familiar with this function and know that that we're used to it as the geometric series. And we can establish this fact, but this will only be valid on the disk centered at the origin of radius 1. And it doesn't tell us that it's analytic on this set. It's just, we get one part of analyticity because this is a power series centered at 0. And so this would just be one part of showing that it's analytic on this whole set. To show it's analytic on this whole set, you'd have to take an arbitrary point, say Z0 in here, and find a power series representation centered at Z0. To get started, I guess we should establish this fact because it becomes very useful when proving it's analytic on the whole set. So why is this true? Well, you might be used to proofs of this, but let's go through it. So you would look at the partial sums, and we have the familiar algebraic formula for the partial sums of a geometric series. So the partial sums are equal to this, and then if we compare this to the function we're considering and estimate it, then we get this expression, which goes to 0 as n goes to infinity, as long as z is less than 1 in modulus, because when we have that, then these terms are geometrically decaying. And then if we don't have that, then we can't say that it's converging. We can later do an argument that it diverges, but for now we've established that yes, indeed, we do have this identity that 1 over 1 minus z is equal to the geometric series for z less than 1 in modulus. Okay, so now what about other points? So now we need to take a z0 in the set C, take away 1, and we need to find a representation of 1 over 1 minus z as a power series centered at z0. So we have to kind of play around with the expression to arrange that. So the only way I can think to do that is kind of throw in a z0 in here and then get rid of it. Let's see, so this is kind of adding in a z0, so I'll subtract out a z0. So this is still equal. And now I'm going to factor out this part, 1 minus z0 from the bottom. Let's see, so I'll have 1 minus z0 sitting on the outside, and that's fine. Since z0 is not equal to 1, there's no issue with that. And now we have this expression. And now we can use the fact that we've just proven that this here is 1 over 1 minus something, and then it'll be equal to a certain series as long as the something is less than 1 in modulus. So we get the following, which, we need conditions here, which I'll state once I know what they are, but this will be equal to this series, and then the conditions are that this part is less than 1 in modulus, which we can rewrite as this expression. So it's valid for z minus z0 in modulus less than the distance between 1 and z0, which is fine because z0 is not equal to 1. And then we have to stare at our expression here and notice that it is indeed a power series centered at z0 because I have these constants sitting in front of expressions of the form z minus z naught to the n. And you could pull this outside factor in here and put in a +1 if you want to. And so this is how you go through to show something is analytic straight from the definition. And what you'll see is that this is rather involved. You have to have a function in mind, and then you have to have a domain in which you think it is analytic. Then you go around to every point in the domain and show that it has a power series representation on a disk centered at that point. On the other hand, it seems, like this is a very strong property. So then if you know something is analytic, then you can prove lots about it. But we want something easier to check to show that something is analytic. And that's where we get into holomorphic functions. But I'll stop this video here just so you can take a little break, and then we'll get into holomorphic functions.